3 that we just sort of wrapped up. We're going to talk in this chapter, obviously, right now about molecular geometry, also periodization in this chapter, and we will also talk about molecular polarity. Again, more so than we did in the previous chapter where we had diatomic molecules. Here we will talk about what we do when we have more than 2 atoms involved, which, as I mentioned before, is a couple of different things that you need to take care of. So molecular geometry refers to really the 3-dimensional arrangement of the molecule and the atoms. We can use our Lewis structures, and really more so how many electron pairs there are, how many non-bonding electrons and bonds that there are to predict the geometry. And really that's the 3-dimensional arrangement of these atoms in this particular compound. There's going to be really 2 types of geometries we're going to talk about. One is the electron pair geometry. And that describes how the electrons are arranged around the central atom in 3-dimensional space. The other one is the molecular geometry. And that is also sometimes referred to as the shape of the molecule. So there will be 2 different names as we go through the geometry. And in some cases, as we will see, they will be the same name. And other cases, the names will vary depending on the situation and really how many electrons we have or what types of electrons are present. So the basis of this is what is referred to as really the idea that electrons, which are negatively charged, do not want to be around each other, but they are, again, forced to be there because they are in the bond. So what they really try to do when you get electrons near each other is they try to get away as far as possible from each other. But in certain cases, they can only get so far from one another. And it changes depending on the type of electrons that are there, whether it is bonding electrons or non-bonding electrons. So whether there's dots or lines in your Lewis structure makes a difference on the overall sort of geometry that we see. So what we do when we talk about geometry is what is known as VSEPR, which is valence shell electron pair repulsion model, hence the abbreviation there. And it's really divided into 2 types of compounds. One type of compound is where we do not have lone pairs on the central atom, so there's no dots in your Lewis structure when you draw it. So it's all bonding electrons to the central atom. And the other one is where we basically have dots. So on this one, we have lone pairs on the central atom, so you'll see dots. And on the top one, obviously, no dots on the central atom. When we do geometry, it is always the center atom that is the most important. So that is always the one that you want to look at, is the central atom in terms of how many electron pairs and how many bonds. So really, when you're trying to determine the geometry, the best way to do it is the number of electron pairs around the central atom, and really how many bonds there are around the central atom. So those 2, what's going to really allow you to figure out the geometry. I would say that most people cannot visually see things in 3-dimensional space in their heads. So a lot of times it really just comes down to memorization of electron pairs, bonds, and the geometries that go with that. So that's probably the best approach as we go through this, is to sort of make a table, if you will. There's also a table at the end and also in your book, but make like a table of how many electron pairs, how many bonds, and the geometries that go with it. And that's usually sort of the best approach. Now, when we do geometry, and only when we do geometry, we do have one really major consideration, which is the first one, is kind of the important thing. If you have any double bonds, or if you have any triple bonds in your picture, we count these as 1 electron pair and only 1 bond. So even though it is a double bond or a triple bond, in terms of geometry, they only count as 1 electron pair and 1 bond. Obviously, anywhere outside of geometry, they count as, more electrons than that, but just for geometry, they're effectively working as one unit. The second one is also important, but it does come up occasionally. We talked about resonance structures. So if you draw a resonance structure for a particular molecule or compound, you could apply this geometry to both of them, and you usually will end up with the same geometry regardless of the resonance structure. So if they are resonance structures of each other, they usually will end up with the same sort of geometries. All right, so let's take a look at really the simplest of all our molecules to do geometry for, and those are diatomic molecules. And diatomic molecules are pretty much just two things, right? So two things together, something like H2, F2, O2, HCl, HF. It doesn't matter if it is two of the same element. It doesn't matter if it's two different elements. It doesn't matter if it has a single, double, or triple bond. When you have a diatomic molecule, there frankly is the only way to arrange two things is a straight line. So the geometry is always linear when it's diatomic. So that is always the geometry, again, for anything that is diatomic. It doesn't, again, matter if it is double bonded, single bonded, triple bonded. It's just two things. There really is no central atom in those guys. And it's just going to be arranged basically in a straight line from each other, which is linear. Now, when we get three or more atoms involved, we do have to take into account the central atom, which is always the important thing. So let's take a look at the first example of that. Here we have an exception to the octet rule. It's an incomplete octet. We have our central atom here. And we want to look at, again, the number of electron pairs around the central atom. It doesn't matter if the electron pairs are dots. It doesn't matter if they're lines. It's just the total number of electron pairs. In this case, there are two. The number of bonds around the central atom in this case is also two. So those are our two bonds, and those are also our two pairs of electrons. When we have something that has two pairs of electrons, the electron pair geometry is linear, also a straight line. When we have two electron pairs and two bonds, the molecular geometry, or the shape, is also going to be linear of each other. It has a bond angle of 180 degrees. So what is happening in this case is our two bonding pairs of electrons are going in opposite directions. They're like, I'm going to get as far away from you as possible. And they end up on opposite sides of each other. And that is basically as far away as they could get in this situation. And that, again, creates that linear shape that we see, which is 180 degrees. So both the electron pair geometry name here and both the molecular geometry name is the same. It is both linear. And again, it has a bond angle of 180 degrees. The next geometry is one where we have a central atom and three things attached to it. And this is boron trifluoride, an incomplete octet as well. Once again, we look at the central atom, which is always where we want to look. It has the number of electron pairs. It has three electron pairs, 1, 2, and 3. The number of bonds is also 3, 1, 2, and 3. Something with three electron pairs, the electron pair geometry name is trigonal planar, also sometimes referred to as triangular. Something with three electron pairs and three bonds, the molecular geometry name or the shape is also going to be trigonal planar. So in this particular case, we have one extra bond than we had before. So what happens is This guy tries to get away, this guy tries to get away, but this guy also cannot get too close either. So they end up in this arrangement. Is called trigonal planar or triangular because it makes a pretty triangle basically when they get away from each other like so. And that again is the electron pair geometry name, and the molecular geometry name is the same. It has a bond angle of 120 degrees, which is that equilateral sort of triangle that happens. The next sort of geometry is one where we have a central atom and 4 things attached. So if we look at a central atom and 4 things attached, like methane here, it has our central atom, which is our carbon. And again, the number of electron pairs is going to be 1, 2, 3, and 4. The number of bonds here will also be 1, 2, 3, and 4. Something with 4 electron pairs has an electron pair geometry name of tetrahedral. And something with 4 electron pairs and 4 bonds. Once again, we added 1 more bond to the mix, which means these guys got to keep some nice separation between them. All these guys got to try to separate as best as they can. Gets a little bit more crowded now that there's 4 things there rather than 3, so they can't get as far apart from each other. The molecular geometry name here is going to also be tetrahedral. It has a bond angle of 109.5 outside atoms. Once again here, both the central atom, the electron pair geometry and the molecular geometry name are going to be the same. If you're old like me and you find an old book, tetrahedron is also a name that's sometimes used during this for this geometry, but most people use tetrahedral nowadays. The next sort of geometry is now going to be one that maybe you haven't seen before. This is going to be our expanded octet. This is something where we have a central atom and 5 things attached. This is our phosphorus, which if you look on the periodic table is right next to sulfur. So again, it can do that expanded octet. When we look at the central atom, the number of electron pairs is 1, 2, 3, 4, and 5 electron pairs. The number of bonds here, 1, 2, 3, 4, and 5. Something with 5 electron pairs is trigonal bipyramidal for the electron pair geometry. And something with 5 electron pairs and 5 bonds, once again, getting a little bit more crowded again. Everybody trying to keep their distance from one another here, trying to spread out as best as they can, ends up in a molecular geometry shape that is also known as trigonal bipyramidal. It actually has 2 different bond angles. It's got a 90-degree happening right about there. And it also has a 120 triangle happening between those guys. So it's got the 120 and the 90 degrees in terms of the bond angle for this. Again, one making more like a triangle and one making basically like a right-hand turn there, or a 90-degree basically. So that obviously falls into our expanded octet. And there is also another geometry that falls into our expanded octet, and that is our guy with 6 around it. And that is what is known as octahedral. And if we look here, the number of electron pairs, we have 1, 2, 3, 4, 5, and 6. Our number of bonds here also going to be 6 in this case. 1, 2, 3, 4, 5, and 6. So something with 6 electron pairs, the electron pair geometry name is going to be octahedral. And the molecular geometry name is also going to be octahedral. This has a bond angle of 90 degrees. So these guys basically make, as you can see here, 90-degree angle happening in this case. Once again here, both the electron pair geometry name and the molecular geometry name are going to be the same for this guy, octahedral expanded octet. Any questions on that there? Up until this point, has the names been different? It has not, and the reason it has not been is because the only type of electrons that we see at this point are bonding electrons. So there are no non-bonding electrons on any of these that we just looked at. So because, again, up until this point, both names are the same. Because no non-bonding electrons. And basically, because they are all bonded electrons, what happens is, as those electron pairs around the central atom moves, it's attached to an atom. So the atom moves exactly the same way. So they end up being the exact same overall shape for the molecule as the electrons are, because they're attached to the atom. So as they move, so does the electrons in the exact same location. And this is not going to be the case as we continue on here when we start to introduce non-bonding electrons to the central atom. What happens when we introduce non-bonding electrons to the central atoms? A couple of things. It increases the I don't want to be around you situation, because we start getting different types of electrons near each other. And it also is able to move a little bit more because it's not an extra atom there. There's just a non-bonding electron. So there's not that extra atom that kind of moves with it. So it gives it a little bit more room to kind of spread out. And what ends up happening as we get these non-bonding electrons in there is it is just the molecular geometry name that actually changes. The electron pair geometry remains the same because there's still the same number of electron pairs around the central atom, but because they are not all bonding electrons, the overall shape or molecular geometry name is actually the one that changes. So let's take a look at some of those and really what is happening when we have non-bonding electrons involved. With non-bonding electrons, there's really three types of interactions that you could have. You could have bonding electrons near bonding electrons, which is what we were just talking about in those few examples up to this point. That is like the best situation. The next best situation is like dots near lines. So bonding atoms near non-bonding atoms in your Lewis structure. The worst situation, non-bonding electrons near non-bonding electrons. They do not want to be near each other. And the news about that is because they're both non-bonding electrons, there's no atoms in the way. So they actually can get quite far away from each other. And again, as those non-bonding electrons are moving, the bonded atoms has to move as well. And again, that's what's going to change the molecular geometry name. All right, so let's take a look at some of these here that you're responsible for. First one is sulfur dioxide. And if we look at sulfur dioxide, looks something like this if you draw it. And if we look at the central atom, which is our sulfur, the number of electron pairs is going to be how many electron pairs around the sulfur in this case? Pairs, there is 1. There is 2, which is the dots. Double bond counts as how many? Counts as only 1. Yeah, so for the purposes of geometry, there is only 3 electron pairs. Again, double bonds and triple bonds count as only 1. The number of bonds in this case would be how many? Number of bonds would be 2. We have our single bond that counts as 1, and once again, our double bond will count as 1. So the number of bonds would be 2. So as I mentioned before, the electron pair geometry, which is based on the number of electron pairs, does not change. So we saw earlier something with 3 electron pairs has an electron pair geometry of what? It is trigonal planar, right? But now what happens is we have bonding electrons near non-bonding electrons. And unlike in the traditional trigonal planar geometry, molecular geometry, we don't have that third atom there. So with the non-bonding electrons, it allows those oxygens to move down, allows the non-bonding electrons to kind of move up, and it ends up in a shape that is known as, for the molecular geometry, I'm going to go with angular. I know a lot of books will go with bent for this one. Some will do bent angular. But for us in here, we're going to go with angular for this one. And I'm going to tell you why. We'll see why in a second here. But angular is the geometry that we're going to go with. Now, it has a bond angle of less than 120 degrees. The bond angles are based off of the electron pair geometry. So if you remember, 3 electron pairs is the 120 degrees. So because it's missing one of those atoms, the bond angle will be just under 120 degrees for this sort of geometry. Any questions on that there? So again, as you can see here, basically our non-bonding electrons go up, these bonding guys go down, and it gets this sort of angular situation that occurs. The next geometry is one where we have a central atom and 3 things attached, but we do have some non-bonding electrons. So if we look here at our picture, we have number of electron pairs is going to be 4 in this case. 1, 2, 3, and again 4, counting the dots. The number of bonds in this case is only 3 in this case. 1, 2, and 3. Once again, the number of electron pairs is based on the electron pair geometry. And since it has 4, the electron pair geometry with 4 is our friend tetrahedral. Again, in this situation, we have our non-bonding electrons kind of going up, our bonding guys kind of coming down and spreading out. And what ends up happening, because it doesn't have that 4th bond, the molecular geometry becomes trigonal pyramid. And that's because it makes like a triangle and this pyramidal sort of shape there on the bottom. And you have sort of a triangle and a pyramid that's happening there. It has a bond angle of less than 109.5. So it's got a bond angle of less than 109.5 degrees. As you can see here, for this particular one, it's actually 107.3. And again, that's less than the tetrahedral bond angle of 109.5. Any questions on that there? Yeah. I'm going to say probably it will show up as like an extra credit question on the exam, right below all of the other drawing subjects you do. So yes and no. If you want to answer that extra credit question, then you need to know it. But it's a good idea to kind of have an idea what they are, at least the main ones. Other questions? All right. Next example is our friend water, which you might have seen before. So our friend water here, our oxygen in the middle. Number of electron pairs going to be 4 in this case. 1, 2, 3, and 4. Number of bonds going to be 2 in this case. 1 and 2. Once again, electron pair geometry based on the number of electron pairs. So this also has 4, which means this electron pair geometry is still tetrahedral. This case of water has all of the worst interactions you could have. It has bonding electrons near bonding. It has non-bonding electrons near non-bonding. And it has the non-bonding near non-bonding electrons. And what happens is, again, these non-bonding electrons kind of head this way, causing our bonding guys to come down. And the result of that is it has a molecular geometry of bent or V-shaped. It has a bond angle of less than 109.5. And in the case of water, as you can see there, it's actually 104.5 degrees, which is obviously less than our tetrahedral. Again, because it's missing 2 bonds, so it has a little bit more room to move because those atoms aren't in the way to do so. This is also why for our SO2 we use angular, because that bond angle is actually closer to 120 versus this bent and V-shaped that's closer to 109.5. So for bent or V-shaped or bent in general, we will use it for this guy. And again, for the other one, we'll use angular because there is really a difference in the bond angles of those two, 120 versus kind of 109. Any questions on that there? Okay. So this is probably the geometry where you stop, but of course we have our expanded octets, so we got to have some expanded geometries as well that have non-bonding electrons. So let's take a look at some of these expanded octets with our non-bonding electrons. Looking at our central atom here, the number of electron pairs going to be 5 in this case. 1, 2, 3, 4, and 5. The number of bonds in this case going to only be 2, 1 and 2. So once again, our number of electron pairs going to tell us our electron pair geometry of trigonal bipyramidal. Now what happens in this case is really our bonding electrons could come out to the sides. Our non-bonding electrons make this kind of triangle type of situation in the center. And we end up with a molecular geometry of linear. So our bonded atoms actually are able to, in this case, get 180 degrees apart from each other. And that is the bond angle, about 180 degrees here, because of that non-bonding electrons coming in a triangle type form to get away from each other as well. That allows those guys to basically spread out. Any questions on that one there? Next geometry is a central atom that also has 5 electron pairs, but only 3 bonds. So if we look at it here, 1 electron pair, 2 electron pairs, 3 electron pairs, 4 and 5 electron pairs. So number of electron pairs is 5. Number of bonds 1, 2, and 3. So once again, our 5 electron pairs means our electron pair geometry is going to be trigonal bipyramidal. And in this case, again, our non-bonding electrons really kind of get out of the way there, causing this guy's actually to make a T shape is what it's called, as you can maybe see the T happening there. And the molecular geometry name there is going to be T-shaped. And it has a bond angle of less than 90 degrees, a little bit less than 90 degrees. In this case, it has our bond angle. Moving to our next one, which is also the expanded octet, we again see here 5 electron pairs around the central atom. And once again, that is 1, 2, 3, 4, and 5. And our number of bonds here going to be 1, 2, 3, and 4. So again, our electron pair geometry based on our number of electron pairs. So we will have our electron pair geometry still being trigonal bipyramidal. And now our molecular geometry, again, the non-bonding electron is going to come out. It's actually going to make this shape, which looks like a seesaw, right? So it's going to make this seesaw shape. This is also sometimes, if you find a book or something like that, sometimes people refer to this as a distorted tetrahedral. So sometimes what this one is referred to as well. But seesaw, I think, is what your book uses. So they would do that. And that has less than 90 degrees and less than 120. So it's got just less than the bond angles that we saw with our trigonal pyramid in this case. The next geometry is our expanded octet into our kind of octahedral arrangement. So these are all of our kind of trigonal bipyramidal expanded octets. So looking at our octahedral situation where we do have our 6 around the central atom. So if we come here, 1, 2, 3, 4, 5, and 6 electron pairs. Number of bonds, though, 1, 2, 3, and 4. So 6 electron pairs and 4 bonds. Once again, 6 electron pairs tells us the electron pair geometry is octahedral. The molecular geometry in this case is our non-bonding electrons go like this, and it actually ends up making a square that's in the plane, hence the name square planar. And it has a bond angle of 90 degrees, as it obviously makes a square there in the plane. Coming through here. And finally, our last geometry for our expanded octet and our octahedral is going to be one where we have basically 6 electron pairs and 5 bonds. I'll spit that out, right? So here, if we look, we have, in terms of our electron pairs, 1, 2, 3, 4, 5, and 6. And our number of bonds going to be 5 in this case. 1, 2, 3, 4, and 5. Once again, our 6 electron pairs tells us our electron pair geometry going to be octahedral. And our molecular geometry, our shape here, will end up being square pyramid. So again, kind of makes a square into a pyramidal type shape that occurs, and we get a square pyramid. Pyramidal. And it has a bond angle of less than 90 degrees. So these are the geometries. Some of them you might be familiar with from the previous class. Obviously, the exceptions to the octet rule, the expanded octet rule, are probably some new geometries for you. I would say, as I mentioned at the beginning, probably the best thing to do is to arrange yourself a table like we just kind of went through, number of electron pairs, number of bonds, and frankly, just memorize the geometries. It's probably just the best way to do it. Here's a table similar to one that you have in the book that obviously does that. By the way, since we are on this page, let's just talk about this molecular geometry and this molecular geometry, right? That is trigonal planar and trigonal pyramid. They are different things, and you should choose the correct one for your situation. You should not just write trigonal on an exam or quiz because it's just going to get one of those. You should not just write trigonal. That was clearly pyramid. I mean, planar, or which one was it? It was one of those, yes. So make sure I clearly know which one it is. Don't, just kind of half write what it is. So like I recommend, you could go back to our slides we just did. This is sort of broken up the same way. Number of electron pairs, really, a number of bonds, which is really what these first 2 columns basically here. That's the number of electron pairs and the number of bonds, basically this column. So that's probably, like I said, really the best way to learn it, which is, by the number of electron pairs, number of bonds. So if we take some of the stuff that we maybe drew earlier or have seen earlier, we take some of these guys really quick as I try to remember all my drawing skills here that maybe I drew. All right. So starting with this guy, what is the electron pair geometry? It is linear, and the number and the molecular geometry is, it is linear as well. Again, we have 2 electron pairs. and we have two bonds, right? So both the electron pair geometry and the molecular geometry are both going to be linear in this case. This guy here has 3 electron pairs, and it has 3 bonds, which means the electron geometry will be trigonal planar, and the molecular geometry will also be trigonal planar, right? This guy right here would be linear. It's just 2 atoms, right? So it's going to be linear regardless. There is no central atom on that. And really there is no 2 geometries. It's really just linear for all of it. This guy right here has 4 electron pairs, bless you, and 2 bonds, which means his electron geometry is going to be tetrahedral, right? Its molecular geometry will be bent or V-shaped, right? This guy right here, 4 electron pairs, right? And 4 bonds, which means its electron geometry will be tetrahedral, right? And its molecular geometry should be tetrahedral as well. By the way, I know it's the same name because there's no dots on the central atom, right? In this particular case. And we drew, I don't remember what we drew earlier, but drew some of those expanded octets. But any questions on how to